As we now proceed to the second session of the evening, I warmly welcome all the participants once again. I now invite Mr. Singaraya Sir, Assistant Professor, Department of CSE AML, to introduce our distinguished speaker, Mr. SaiRam Palabindale from TSARO Labs, who will be delivering a session on homomorphic encryption. Over to you, Singaraya Sir.
Good evening, everyone present here. This is Y. Singaraya, Assistant Professor in AML Department, KMIT College. It gives me a great pleasure to welcome you all to today's session of our Faculty Development Program on Homomorphic Encryption. It is a great honor and privilege to introduce our esteemed speaker, Mr. SaiRam Palabindela, who currently serves as a security researcher at TSARO Labs, Michigan, USA, and as a security solution engineer with Simlan. Mr. SaiRam holds dual master's degrees in information assurance and internet architecture from top US universities. Mr. SaiRam sir has received specialized training from FEMA under the US Department of Homeland Security in cyber incident response, ICS, operational security, and more. Mr. SaiRam sir collaborates with global organizations like ISACA, CSI, IEEE, FTCCI, and the Internet Society. He is also active in social impact, working with the NGO Now Foundation to promote digital literacy and well-being. Mr. SaiRam sir trains police departments, agencies, and professionals in cyber security and partners with MHA, ICSC Foundation, and NCSAI. Mr. SaiRam sir holds several key certifications, including Certified Cyber Security Expert, International Forensic Science, Certified Cyber Intelligence Investigator, CCII, Certified Ethical Hacker, Microsoft Azure Fundamentals, and Security Expert. Let us warmly welcome you, sir. Thank you.
Thank you, Mr. Singaraya Sir. With a great respect, I now welcome our speaker, Mr. Sairam Palabindale, to take over the session on homomorphic encryption. Kindly take over the session, sir. Thank you.
Hello, everyone. Good evening. So first of all, thank you so much for having me here today. I'm very glad to be part of this session and respected, doctorates and, the professors from different backgrounds. I would like to share my knowledge on this homomorphic encryption. Mostly, I'm from information security background professional, and I'm into cybersecurity domain. I'll try to keep things as simple as possible. And in the last, we'll try to have a small quiz as well. And let's dive into the session. Anybody would like to take 1 minute quick break before we start? Because I know you guys are being there online for more than 1.5 hours. If you don't require, we'll continue.
Continue, sir.
Okay, sure. Okay. So as mentioned, just a quick confidentiality note, whatever we are discussing, it's solely my perception, and whatever the information that I'm going to share, you can use it for educational purposes, and it's just non-disclosure confidentiality note. And today agenda, we are going to take a look at why the need for the data privacy, which we are going to cover some few of the foundations that involves, and what are the vulnerabilities in the data in use, and which it indirectly covers the homomorphic encryption. And we also take a look at some of the use cases and challenges, and if possible, we'll say some of the use case and examples. Okay. So Before starting, I just want to ask a quick question for the audience. So, can anybody explain me the small difference between hashing and encryption? Quick answer, please. Anyone from the audience? What is the difference between encryption and hashing? Hello, ma'am. Hope I am audible.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Hashing is
Yeah.
not reversible, but
Hope.
encryption can be reversed with the proper key.
Sorry, can someone please repeat that? I
It's not
missed it.
reversible, but encryption can be reversed with the proper key.
Okay. Hashing is not reversible, but encryption can be reversible, right? Any good example for hashing, please?
Sir,
It's not
excuse
reversible.
me. This
Let's say 512, SHA-3, KEKAK, MD5.
Yes, sir. Any real-time day-to-day example, please?
sir, hashing used for the integrity and encryption used for the confidentiality.
Okay, exactly. So the best example for hashing is your PIN codes, right? Your password for any account. So they're stored in the hash values, right? If you try to log into any system, that's a better example I can say. And encryption, we see our day-to-day end-to-end communications by using WhatsApp or any other application which implements end-to-end, which has the encryption and decryption process. Okay, so so let's see the basics of encryption. Like as we see, the analogy itself explains. It takes a plain text and it uses some kind of algorithm and it converts into a ciphertext, right? So the main goal is to implement the confidentiality. As you see, the definition itself, the process of converting information or data into a code ciphertext to prevent the unauthorized access. And as you see, the core components includes some of the plain text, ciphertext, and the algorithm, which also has a key, right? So the basic encryption process works like this. But if you see in depth, the encryption also covers two subsections. One is the symmetric versus asymmetric. Uh, so if you see the symmetric encryption, it uses a single shade key for both the encryption and decryption process. Like the examples, if you see AES and DES encryption methodologies, if you see the analogy, like you can have a house key, but the same door can be locked by any person. Like you can just close the door and lock it, but only the person who has the key can enter into the room, right? And some, if you see the pros, they are very fast in nature, and if you see the cons, you need to securely share the key in the first place if you want to unlock the any this break this encryption. So the here the main problem is the key distribution, how you are going to handle the key, right? So that's the reason we have the asymmetric encryption. You can see it has a pair of keys, which is public and private key. Like mostly it's kind of a mailbox on the street, like anybody can drop the mail in it, but only with but people with the public key in the back end, they can open and put the envelope inside the box, but only the private key you can open it. Usually this system is not implemented in India, but if you see in Western countries, this process is implemented. The best examples are the RSA and ECC encryption algorithms, which solves this asymmetrical problem. And if you see, it solves the main key distribution problem, right? And but when it compares, it is much slower than the symmetric encryption. So now we have seen the symmetric and asymmetric encryption. Here is just a pictographical representation how it uh, works. If you see on the left side, to encrypt and the decrypt, we have the shared secret key. It's a single key. But on the right side, if you see, the two keys are needed, right? Recipient's public key and recipient's private key to encrypt and decrypt the messages. Hope this pace is good enough. Are you guys following?
Yes, sir.
Yes,
Yes, sir.
sir. Yes,
Following.
sir.
Okay. Okay, thank you. So moving on here, I just want to show a small difference between the symmetric and asymmetric key encryptions. So mostly if you see the length of the keys, you need to be consider. Mostly the symmetric key, we use 128 to 256 bit. But if you come to the asymmetric key, the length of the key will be like 2048 or higher. And it solves the most of the confidentiality, authenticity, and non-repudiation methodologies. So examples for these symmetric key encryption are 3DES, AES, and when it comes to the asymmetric key, we have the Diffie-Hellman, ECC, DSA, RSA are the most famous examples for this asymmetric key encryption. And when it comes to the implementation of the keys, right, we need to understand which one we need to choose. So choosing between symmetric and asymmetric encryption depends on several factors. One is like speed and performance. If you see, symmetric encryption is more speed, and asymmetric encryption is more secure if you compare, but it depends on the use case, how you are going to use both of them. And depends on the security level, like how you want to share your keys. As asymmetric encryption is more secure because it doesn't require any kind of sharing of the keys, right? And some of the use case and applications, if you see, the VPNs, everyday VPN tunneling, all this concept will be used by the symmetric. But if you want to implement more secure SSL TLS, now we are using TLS 1.3 version. So in this, asymmetric encryption plays a major role, and especially these things are also used in the bitcoins and cryptocurrency transactions. And management key also plays a major option for choosing these keys. Between the sender and receiver, how you are going to manage the methodology, it matters. And hybrid approach is one of the area where most of the vendors use these days. Depends on the security of the system. So these are the few factors where you need to understand how to choose between the symmetric and asymmetric. These are the regular day-to-day end communications that we are seeing. Um, so moving on, there might be a big question, right? What is the next? We are hearing about symmetric, asymmetric keys, and after that, homomorphic encryption came into the picture. So mostly, if you see, the main problem it is solving is trying to, do the data analysis when they are stored in uh, stored in a physical format. I mean, not only in physical format, any format. Like if you see the symmetric and asymmetrical encryptions, they protect data at rest and also in the data and transmit. But if you want to do some kind of mathematical computations, which are data that is in use, then you must have some kind of encryption methodology, which homomorphic encryption is going to address it. So here, the big problem, right, that we see, data in use is very vulnerable. So when whoever is using the data, if the data is in plain text or some kind of encryption is being implemented in it, and someone can even decrypt it to analyze the data, then that is very vulnerable in nature. So here, data at rest, basically it might be stored on a hard drive, which can be encrypted, but again, it needs to be decrypted to do the analysis in case of symmetric and asymmetric. But whenever the data is in transit, it can be encrypted by using the TLS protocols. And when it comes to data in use, the traditional methodologies won't work. You need to have some kind of computation that need to be implemented. So this vulnerability can be addressed by using this uh, homomorphic encryption. So if you see the cycle, decrypt, compute, and re-encrypt is this is the weak link that you see in your day-to-day communications. So before that, just to understand, we have the encryption versus the computation. So if you see the symmetric encryption, AES or DES model, they are very fast in nature. They're secure for storage and transmission, right? If you see the asymmetric encryption, the RSA and ECC, they are like good for digital signature implementations, right? So whatever the digital signatures, the registers, or all these things are implemented, they solve this problem. So if you see the problem here, whoever decrypts get access to your raw data, right? Especially in your cloud environments, this means you cannot trust your third party vendors or whoever having the hold of the sensitive data. So even if your SLA terms in your cloud mention that your data is encrypted or stored in multiple layers of defense in depth concepts, you cannot solely rely on, because you don't have any physical access to those data servers. So it is a quite challenging when it comes to the cloud environments, how you are going to implement these things. So before moving on, I just have a quick question. Can anybody give me the difference between privacy and security? Anyone, please? What is the difference between privacy and security? Hope I am audible, guys. Hello?
Audible, sir, audible.
Yes. Can anyone give the difference between privacy and security, please?
Privacy means protecting our personal information.
Okay.
Coming to the
Security?
security means we have to, for example, we have a company like that. We have to secure the data. That is a third party.
Okay. We'll park that. Any other definition, please?
Sir, privacy means just like preventing from disclosing the sensitive data. That is privacy.
Okay.
And security is like protecting the data from accessing by unauthorized users.
Okay, right. So exactly, security is like protecting the information by using any means necessary to protect the data falling into the wrong hands. But the privacy, right? Privacy, that is something about you, which defines something about you. So whether it might be your full name, whether it might be your PAN card, others, something which relates to you is a privacy thing. So there's a small thin line between these two terms. You just need to go through because most of the integrity factors and all these things when we solve this encryption methodologies, right? So we need to understand what these things are really solving in nature. So here, if you see, here are few advantages that if we implement the homomorphic encryption, the homomorphic encryption can perform the operations on the encrypted data without decrypting it. So whenever, if you see there is some encrypted data which is residing on a server sitting somewhere in remote areas, you don't need to give your decryption keys for someone to analyze that data. So with the help of homomorphic encryption, that data can be that data can be analyzed, do the computations based on the use case or the requirements. And similarly, when it comes to the cloud, right, as we discussed, the third party analytics provider, if someone wants to do the computations on a data blindly, this homomorphic encryption will be the advantageous one. And most of the time the data owners decrypts the results, but if the computation was done on the plain text, it is less of no secure, right? So this is the main advantages of it. And why it matters. So if you see the data privacy in cloud computing, some of the use cases, if you see here, right, the data privacy in cloud computing, a hospital can send encrypted patients data record to cloud for statistical analysis. The cloud never sees the actual records, because when you see the requirements of the data frameworks, right, there is a layer of protection that covers the personal information of every patient record. which is indirectly mentioned in the HIPAA compliance. Like if you see the second point, the regulatory compliance, for most of the GDPR, HIPAA, DPDP, the data protection laws in India, most of the homomorphic encryption enables the processing of these data uh, by using the data minimization without unauthorized access. So this is one of the main advantage for many big corporates to do the data analysis without decrypting the original data. And the other use case is the secure collaboration. Suppose if two companies are jointly going to compute on encrypted data, like for fraud detections and supply chain optimization, your business can implement this encryption methodology for sharing of your data without disclosing it. And some of the AI and ML models to implement increase the privacy in machine learning, most of the latest methodologies are using this homomorphic encryption. So here, if you see the simple comparison table, like if you see on the left side, we have the aspects of the data and symmetric, asymmetric, and homomorphic. If you see symmetric encryption protects the data at rest, protects the data in transit, but symmetric and asymmetric are not going to solve the computation on the ciphertext. But when it comes to the homomorphic, this is the biggest advantage, that any use case can be used to do the computation on the ciphertext, which indirectly preserves the privacy of the data in nature. So
Sir,
sorry,
sir, I have
sir,
a doubt.
please. Yeah,
It's
please.
privacy preserving computation that allows is homomorphic encryption only, or any other methods are there?
I mean, so far I'm aware of this encryption, madam, but I think there are other encryption models as well. I can give the data after the session, but I'm not
Okay.
sure exactly at this moment. But I read some technical papers which they implemented it, but it is not vastly used in the real-time applications so far.
Yeah. Yes,
Yeah,
yes.
yeah.
Okay, sir. Thank you.
Okay, thank you. So we are discussing about this homomorphic encryption, right? So let's get into this. So homomorphic encryption in simple terms is a cryptographic approach that permits the information to be processed even as it remains in an encrypted form, right? Like unlike the conventional encryption, which calls for the statistics to be decrypted for any significant operation, homomorphic encryption performs the computations to be performed at once on encrypted statistics. So as we discussed, so most of the encrypted data no need to be decrypted when we are using this homomorphic encryption. And this cryptographic methodology will solve most of the computational issues to preserve the privacy aspects. So here I have a small video just to watch for quick 2-minute video.
Public key encryption scheme. So you can think of a public key encryption scheme where, encryption is a public process. You can think of it as slamming a door that just clicks, and it's locked. And then there's someone else has the secret key. So anybody can slam the door shut. But the person that has the key has to come and open it up. So then a homomorphic encryption scheme is one where somehow magically this you can think of it as a glove box. So basically anybody can come and they can stick their hands inside the gloves and manipulate what's inside the locked box. They can't pull it out, but they can manipulate it. They can process it. They can take raw materials and produce a necklace or something inside the box. And then they finish, and then that same person has to come with the secret key and open it up, and only they can extract the finished product out of them.
Hope you guys followed. So it's just a kind of, if you see in any technical laboratories, what they exactly do. If you want to operate on something which is critical in nature, you will put it in a chamber with, you have proper gloves which gives access to that specific product which you can operate on, but you cannot, really touch or feel that product. And if only the data owner, or in this case the data owner who has access to it, can only take those items and do feel those things, right? So similarly, the cloud lockbox, you can compare it to your valuable data as valuable gems, something which you put it in a transparent box, where a jeweler or someone who could, as a cloud server, if they want to work on them, they can just use that data inside, but they cannot see the original data. And especially this homomorphic encryption scheme, right? This is kind of acting as a separate layer, or you can see it as an encapsulated layer which will be protected. So if you see the core property, right, how it do that: encapsulation A O plus encapsulation B, which is equal to encapsulation of the A plus B. This data which you are going to see, most of the time the results will be like this. And moving on, if you see the applications of this homomorphic encryption, one of the thing is secure outsourcing. So the compelling use of the instance of this encryption to delegate the computation to untrusted servers, right? So the good example is your Gmail. So usually when you store your Gmail data, everyone, whenever we create the email account, we get a 15 GB of data. But in the real use case, we never get 15 GB. As we start, storing the data, then the increase will be the limit will be increasing. But if you see in the back end what exactly happens, it's not a private cloud, right? So most, why it is free in the first place? You are not paying for it, so that means they're not going to keep your data in private cloud. When our data is not in the private cloud, what happens? The other cloud is public cloud. So it should have certain kind of protection methodologies, right? Right. So when this data, whatever the data which we store on our free accounts in Gmail, Outlook, you take Hotmail, Reddit, all these data which resides in the public cloud servers, they are doing analytics on this data. So whenever you take a picture or you discuss something on this, by using your mobile devices, which keeps on listening, right? So all this data will be dumped into the public cloud servers, where they do this analysis by using this homomorphic encryption without decrypting of the data. So similarly, if you can ask me whether WhatsApp is doing it, yes. So WhatsApp says that your end-to-end communications are encrypted, but if you see how that company is making money out of WhatsApp, so by using these algorithms, they do run all these computational methodologies to do the computations on the data, and they do the analysis out of it and try to focus on the specific. So whenever you see a festival coming in, or else there is a event, special Father's Day or Mother's Day, India is the only country which shares the messages mostly throughout the between the people. So they know that these servers are going to be flooded with much data, and this data needs to be analyzed to capture the user behavior analytics. So to understand this, they use this encryption methodologies to understand and analyze the user behaviors as well. And some of the other applications, if you see privacy preserving of the data analysis, so this also increases the privacy preserving methodologies. As you see, most of the data preventiveness is paramount for when it comes to the big organizations, and even for the government. If you see the GDPR and other Western countries, they have their own protection laws, which they implemented more than 5 to 6 years before than us. And these things are implements all these encryption methodologies to prevent those aspects. And some of the other two are the confidentiality and secure data sharing methodologies that which we see in our day-to-day use cases. And here are some of the use cases I just want to point out. In our Indian sector, we see other data analytics. Like most of our other details holds the biometrics and demographic data of the citizens. But when it comes to it, you cannot just give the data directly to even to the government to do the analysis, right? So that's why homomorphic encryption as a solution, uh, it shares the data which is in the encrypted format, but it shares along with the RBI and other companies to do the analytics, especially the credit bureaus. The second one, right? The banking and the financial fraud detection methodologies, where the credit bureaus need to understand the financial risk, how the money is moving from one account to another account, and how it is exposed to the real world. So these type of solutions can be worked by using these algorithms. And if you see the HIPAA one, which we already discussed, to be compliance with the DPDP laws in India and also HIPAA laws in the US. So these things as a solution, like if you see the COVID trends, right? Even when we share the data, right? Most of the encrypted data which we share will be authenticated by using the SHA algorithms. But moving on, we have this multi-institution medical researchers that are going on are also using this kind of privacy related homomorphic encryption techniques. And some other use cases will be the smart cities and cross industry collaborations, and some of the insurance companies use these methodologies to implement. You can just go through the reading. I will share the presentation. So moving on, here we can see, you may ask, what are the different types of homomorphic encryption, right? So here I see there are few different types which are involved. One is partial homomorphic encryption, and there is fully homomorphic encryption, which is FHE. And the third one is somewhat homomorphic encryption. And the other three are not much utilized, but it depends on the use case: bootstrappable, homomorphic, approximate, and lattice based. So depends on the use cases, we are going to utilize these type of encryptions. So let's dive in. Here, if you see the first one, partially homomorphic encryption, here it is used for specific set of operations to be carried out. Like examples, the additive homomorphism, right? So if you want to add certain kind of data and do that, so e to the and e to the b, if you add e to the a plus b or a minus b without any decryption, you can do that additive homomorphism. And multiplicative can be done, and also comparison can also be done. So multiplication, division methodologies, addition and subtraction methodologies of the data can be done by using this partially homomorphic encryption. So some of the additive homomorphism, you can see the Palier crypto system. Like if you see the decryption of the encrypted data M1 into encrypted M2, that can be equal to M1 plus M2. There's algorithm that you can see. If this is the same use case which is used in US voting system, e-voting system. They have the physical ballots and also the electronic voting systems as well. This is the use case where they widely implement this in the real-time use case. So and other example is the multiplicative homomorphism. So when it comes to the unpadded RSA, so you can do the multiplication process in this. This only works with the textbook RSA, right? Secure padding and OAEP models can be used in the breaking of this homomorphic property. And the next one is fully homomorphic encryption, the FHE. It can be used to utilize a maximum powerful algorithm that I can say. It uses the neither the multiplication operations and nor the and or not or the Boolean operations that which can be used in these methodologies. And FHE also permits the computation on the encrypted data without decrypting and making it a extraordinary stable. However, the computationality is intensive. So fully homomorphic, if you see the picture on the right side, it's a generalized picture. Like if someone is requesting of that decryption key, if you are using the query of cipher PKs, and using by if you want to evaluate by using some kind of search engine to do that evaluation on that specific data, and after that you can store the result and you can again request for that specific data. So some of the best examples for that FHE is encompass the Halvi Vaikunthanathan DGHV scheme, like DHK Gentry Halvi Vaikunthanathan is a scheme that mostly utilizes this fully homomorphic encryption. And some of the mathematical foundations that this modern FHE will cover are the lattice-based cryptography, which is there, which we are going to discuss further, and some of the post-quantum security issues, like unlike the RSA, these lattice problems can be, uh, I mean, they are believed to be resistant for quantum computers, but most of the time now, if you see, the Chinese already cracked the AES 50-bit, and they also claim that they are soon going to crack the 100-bit AES, right? So with this powerful quantum computer, it's just a inevitability of the time, right? So if you see the next 5 to 6 years, whatever the time frame which we have left, they are going to come up with the most problem solving cryptographic methodologies to break these encryption models. So post quantum security also plays a major role that you can look into the one of the next career options. And some of the four modern FHE schemes will be, like I discussed earlier, BFV, BGV, CKKS, and TFHE. Like these names are very specific, picky in nature, right? Brakaski, Fan Vactoran, Brakaski, Gentry, Vaikanthanathan, and Cheon Kim Kim Song. Like if TFHE is the fast fully homomorphic encryption over the torus. So these are the some of the top FHE schemes that are mostly considered. I just give a small data to comparative of these summaries, like what exactly these use. If you see, the primary data type will be integers for BFV, BGV, and real complex and booleans for the TFHE. So you can use these mix and match combinations if you are using to solve any kind of specific the encryption, fully homomorphic encryptions. So there are some use cases that I discussed here as well. Ideal use cases to extract the statistics from a database queries, and some of the deep arithmetic machine learning algorithms can be done by using this FHE algorithms. So coming to the somewhat homomorphic encryption, these are permitted for limited wide of applications. It is not widely used so far, but these things, without these things can be operated without compromising the security of the data, right? So whenever it gives the more stability between the security and the computational performance. And if you see the third point, the SHE schemes includes the Pyler crypto systems, which helps the additive homomorphism, and the LGAML crypto systems, which helps the multiplicative homomorphism. So these two systems will be, utilized in this SHE methodology. So you may ask me the next question, like why she is only somewhat, right? So in this, if you see, the answer is the noise. So whenever we see all these encrypted data, whenever we try to decode it, the noise is the biggest issue. So modern homomorphic encryption schemes, right, based on the lattice cryptography, they add a small amount of the random noise during the encryption to ensure the security. Sometimes it can be considered as a boon and also a bane. So noise growth, if it is too much, you cannot, get the output exactly, where if you should have a certain kind of threshold, right? The cumulative noise grows too large, it corrupts the data, right, in the first place, and the decryption will fail in this methodology. So that's why the she scheme will have the finite computational budget before the noise overflows. So you need to understand those limitations for the noises whenever you are using this she computational algorithm. And moving on, we have the bootstrappable homomorphic encryption, right? So bootstrappable encryption is a version of the FHE that consists of a mechanism for refreshing the ciphertext. So correctly, if you resetting the noise delivered at some point of homomorphic operations. So you need to understand that kinds of ciphertext that needs to be reset to reduce the noise and do the operations. And some of the FHE schemes to perform the vast range of operations as long as the ciphertext was periodically refreshed. So it needs to be, based on the timestamp. Whenever you are generating ciphertext keys, that needs to be periodic in nature to specific frequency or the interval that that you set up. It On the right side, if you see, it's a standard, bootstrappable homomorphic encryption methodology, where you see on the right side bottom, the keys are going to be, changed in a specific interval of time to increase the, increase the strongness in the encryption methodology. So the BGV scheme is the best example for this bootstrappable homomorphic encryption. This scheme can be, considered for a specific rotation of the keys whenever it is needed. Especially these are used in IAM use cases, identity access methodologies, by using the VPNs and IAM methodologies. By sharing, by rotating the keys for every specific interval of time, this encryption methodology will be, very strong in nature. So the next question is like how bootstrapping works, right? So bootstrapping is works by using the homomorphic encryption to decrypt itself. Some of the encrypted versions shares the secret key. Encrypted secret key is like the bootstrapping key. The server takes the noise, like the ciphertext, and encrypt it with M. So it's a kind of a computational. If you see, C underscore fresh is like evaluation of the decrypt circuit and the encrypt secret key with C. So C is the refreshing key that needs to be refreshed with every certain interval of time to reduce the noise. So this, which will low noise encryption to the original message. That's how we get the original message. And moving on, we have the approximate homomorphic encryption. So in this approximate homomorphic encryption scheme, we prioritize the efficiency over the ideal homomorphism. So they permit a huge variety of operations like encrypted data and, over a small errors within the consequences. These schemes are beneficial programs where, inaccuracies can be, tolerated. Some of the examples comprises of the approximate number homomorphism ANH and the homomorphic encryption for the logistic regression HELR schemes. So this is the approximate homomorphic encryption. This is not widely used in nature. And moving on, we have the lattice-based homomorphic encryption. This is widely used for many use cases. Like most of the cutting-edge, technologies use this. So if you see in the lattice-based, right, it's one of the strongest safety residences, and it is also fail-proof for quantum attacks, right? So that's why it is pretty much used in the real-time use cases. Let's see. So some of the important terms that you need to understand in the lattice This one is first one is lattices. Lattices are basically the thought of a regular spiced grid of set of points that are infinite in number. If you consider on the right side, if you see the images, right, these are the basically the points which are infinite in number. If you can see the set of points, and the second one is a vector. A vector is a point that you can see, if you see the coordinates that are converging from, as example here, it's mentioned 2, 3 is a vector having the coordinates of -2 and 3. Like the axis x and y, which can be grown in the both ways, right? So you need to understand the vectors. And the third one is the basis, right? Lattices have the larger objects, but computers have a finite amount of memory. So mathematicians and cryptographers thought of a second way to use the lattices. So these are the three important terms that you need to understand in the lattice-based homomorphic encryption: lattices, vectors, and the basis. And these things are classified, especially the lattices are classified into three different categories, right? So one is aperiodic, chaotic, and periodic. So aperiodic lattice is a pattern that doesn't repeat exactly, but there are no overlaps and gaps. But when it comes to the periodic, right, it repeats again and again with no overlaps and gaps. But when it comes to the chaotic pattern is a pattern with overlaps and gaps, introducing randomness in your equation. So the random factor will be brought by the chaotic. So these are the three categories that you need to remember: aperiodic, chaotic, and the periodic. So here there is a small example. Like if you see, if an attacker is asked to pick between two random points, it will be very difficult to determine which point on the 10-point lattice patterns leads to the 100-point lattice. So thus, if you know the key, you can easily decode the message. So it is very hard for any attacker to understand how these random patterns will go in different directions. And even if you find the right point to initialize the data vectors, it is very hard to break down and decode the original message. So that's why lattice, this methodology, homomorphic encryption, is used widely in the upcoming use cases. And if you see, as we discussed many of these things, right, the biggest elephant in the room are the challenges. If you see, one is the performance overhead. So this is the biggest challenge. Like when it comes to the computations on encrypted data are significantly slower. Like if you are multiplying 1,000 times to 10,000 times, that too on a plain text, the performance will reduce drastically. So this is one of the biggest challenge that we see when it comes to the encryption methodologies. And another one is the analogy. Like if you see, asking someone to perform a surgery while wearing thick winter gloves, it is impossible, right? So the analogy itself, like when you see, we discuss different sub use cases or the naming conversions that we see in the cryptography process. The analogy itself is very tough to remember all these names. And the third one is the ciphertext expansion. Like encrypted data is much larger than the plain text data. So a single number can become kilobytes or megabytes of the ciphertext. So it is it is very burden for any database to handle that much of data when it is converted into ciphertext. The load will be increased and the performance will be reduced. And if you see the last one, the complexity, the implementing of the homomorphic encryption schemes is likely highly complex and requires the specialized cryptographic knowledge. And this cryptographic knowledge is not widely used. The number of people which understand these type of cryptographic concepts are very less in nature, and only doctorates or laurels can understand these to implement these challenges to solve the real-time use cases. So it's also very complexity in nature to understand this. So these are few of the challenges that I see in this encryption. So actually, I have a small hands-on demo for that. So But unfortunately, I'm on my office machine. I cannot install the Python libraries. I just want to give a description. I'll just give the code for you also to implement this. I will share it with the respective faculty members. So here we are going to use this tool, right? The Seal Python. It's a Python wrapper for Microsoft Seal. It's a simple encrypted arithmetic library which we are going to use. So here what we are going to do is generate a public key and a private key pair, encrypt two numbers and multiply them, and also decrypt the results. So here is a Git URL that I would like to share at this point of time. So if you go to this Git. One second. I think my screen is paused. Let me share. So this is a Git repo which consists of it. So Microsoft Seal is an open source, it's a MIT licensed homomorphic encryption library that is developed by Microsoft for some of the cryptographic research that they did. So here are the some of the build commands, like which is the latest version that you can see. You can do it on the Windows, and also you can host it on your Docker. And here are the few steps that they mention. And I will also share the list of steps. um, One second. So here is the Python code that to generate this, how to do the setup. If the setup will have this set of steps, how you are going to do it. The second step is going to be the key generation, how you are going to generate the key. And unfortunately, it's not loading here. Let me
You
scroll
are
it.
unable to see the code you are typing, sir.
Okay, one second. So I just put it on a Word document. Okay. Here, this is the repo link. Okay. In the first setup, you need to import that library, Python library, and install it. Here, in the second step, we are going to do the key generation. Okay. Key gen, the seal is going to generate a key generation. You're going to see the public key and the secret key. And here we are going to implement the multiplication process, right? So this multiplication can be implemented by this. Here you are going to give the encryption numbers, how you want to do the define the value for this. You can use here the printing of that encryption in the plain numbers. And here the encryption plain number 2, this encryption encryptor going to encrypt the plain numbers, and it's going to print it. So in this homomorphic computations, most of the time the server is going to perform the computation on the encrypted data. No, right? So it's not on the plain data. It's going to do the encryption on the encrypted data. So here you can add it. You do the homomorphic addition, and even you can do the multiplication process. Here I define the steps. You can implement in your machines internally, and you can also do the decryption methodology. So how you are going to decrypt the result? You are going to decrypt the result, not the original data. So how you are going to decrypt it? It is well defined in these steps. I'm going to share these steps with you. You can try installing this in your local machine, and let me know the result, how it's going to take, because it itself takes more than half an hour of time if you do it. Unfortunately, I'm on my office machine right now. Um, okay. So here, we have some few of the summary items. What we take a look into: the traditional encryption leaves the data vulnerable. So when it is being processed, the solution is the homomorphic encryption, which allows for the computation of the encrypted data, which it majorly closes the security gap, right? The trade-off will be like, unprecedented privacy, and some of the significant performance costs can be reduced by using this homomorphic encryption. And the future holds the hardware acceleration, like FPGAs and ASICs are being designed specifically for homomorphic encryption, because it's a most promising edge that most of the real-time hardware systems are going to be worked on. And some of the better algorithms are also coming into the picture by using this homomorphic encryption. The list is expanding. There is a lot of research going on in this area, and some of the standardization efforts are also being done. So some of the homomorphic schemes, they are widely the nations are trying to implement as part of a AES or SHA. These methodologies can be replaced in future with the homomorphic encryption methodologies. So these are the some of the future outlooks that I will say. And moving on, I would like everyone to take a small quiz. Okay. I'll just share this link in the chat box as well. One second. So I hope everybody can access the quiz. You can even, scan this QR code, or else, you can uh, click on the link that I shared in the chat box. There are 20 quick questions which covers the most of the topics that we discussed today, which also closely work with the real-time use cases. Everybody can access it. Please confirm.
Yes, sir.
Yes, sir. Yes.
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 For this, what I'm going to do is I'll just put a 10-minute, timer on the screen for now. So just please go through the quiz. Let me know if you are facing any trouble. I'm going to start the timer. Hope everybody can access the quiz. Let me know if you are having any trouble. Five more minutes. Hope the questions are interesting. Last 2 minutes, guys. I just want to give a heads up. Anyone completed it?
Yes, sir, completed.
Done, sir.
Okay. How are the questions? How do you feel the questions?
Quite easy if I have listened to the thing like properly, it's quite easy.
Okay. Let's wind it up, guys. I know it's already 9 o'clock and it's getting late. So anyone have any questions so far in this homomorphic encryption?
Sir,
Yes, please.
so fully homomorphic encryption are these six types you mentioned, lattice based. So
Yes, ma'am.
when I come to across the literature on lattice based, I could find somewhat homomorphic encryption, fully homomorphic encryption, all these kinds, right?
Yes, ma'am.
Is it separate kind of lattice based fully homomorphic encryption, or lattice based is the mathematical background that they were taking, and homomorphic encryption that they are building on it?
Lattice based will be, now the use cases are increased, right? So what they're trying to do, as you mentioned, it is going to be the mathematical computation method that they are going to take it as a base. And based on top of that, they are going to implement the algorithm to solve the use cases.
Okay. Sir, other than lattice based, any other mathematical hard problems that they were having to implement this homomorphic encryption?
Uh, So far, not that widely used that I come into picture, but lattice based is the only one which I see. But when you see these schemes, right? Mostly, now it is focused on mostly the error correction and the reduction of the noise only. But BVG and the CKSS is also one which they are using simultaneously to address these issues.
Okay, sir.
Yeah.
Thank you.
Thank you. Any other questions, please? Okay. If not, thank you guys. Thank you so much for your time today. I'm available only on LinkedIn, and I have a small website, SaiRam.digital. You can please visit. And if you have any questions, please feel free to ask me and reach me out. Uh, uh, Thank you so much for your time today. Over to the organizer, please.
Thank you very much, sir. Thank you. Thank you, sir, very much for giving a thought-provoking and engaging session on homomorphic encryption. We have gained an insight on difference between hashing, encryption, and privacy and security. And you also highlighted the detailed information on types of homomorphic encryption, telling the difference between why which type is useful and why. So it was very useful for all the participants, I think so, sir. And you have also highlighted how the bootstrapping works. And one more, the important thing that we liked is seal Python for homomorphic encryption. So the information that we get again was very nice, sir. Sir, one thing I want to know, you are given one URL related to that. So
Yes.
can we get that URL so that participant can work on that?
Yes, ma'am. I will share the Git repo link and also the
Okay.
step-by-step process. Along with that, I see some people are asking for the question and answers as well. I will also share this question and answers for the knowledge
Okay.
sharing. Sure, I'll do
Okay.
that after the call.
Okay. Thank you. Thank you, sir.
Yeah.
Thank you, sir, for your session highlighting on one of the most promising direction in the secure data provision processing. On the behalf of organizers and participants, we deeply appreciate the time and insights you have shared with us, sir. Thank you once again, sir.
Thank you. Thank you so much, ma'am. Have a good night,
Uh,
everyone.
Thank you, sir.
Anything else, ma'am?
Anyone has any doubt? Any questions? Participants? Thank you, sir.
Yeah, okay,
With
ma'am.
this,
Thank
we come to the conclusion of the day 3 of our FDP. We have two enriching sessions today. The first on quantum error correction course by Dr. Swati Mumadi, and the second on homomorphic encryption by Mr. SaiRam Palabindela. The feedback link for each session have been shared in the chat. Kindly fill and submit them at your earliest, participants. Now, on behalf of the organizing team, and I sincerely thank today's resource person for their valuable contribution and all the participants for your active involvement and enthusiasm. Thank you, sir.